Okay, so just now your orthographics, you see your dx, dy, dz here got value. You compare. Okay, see here, dx, dy, dz. And then your last row is 0, 0, 0, 1. Okay, so for perspective projection matrix, okay, you have your -1 here. And then your formula is at the negative z, the z column here. Okay, so this one for orthographic is at this side. Okay, for perspective is at here. Okay, put -1. So your when you put -1 here, mean your z-axis will be reversed. -1 mean reverse. Okay, positive is front. You have -1, your value will be reversed. So any vertex, you go and multiply with your projection matrix for perspective because it's -1 here. So if your original value is here, it will flip in the y. Okay, your y-axis will be reversed. Okay, that's why you have to be careful. Okay, a lot of you after change to perspective view, you get your z-axis reversed because of this -1. Then you are confusing. Okay, so a lot of you will say, Miss, I draw the robot, but it's facing the back. You see the back of the robot, it's not the front. Okay, because your z already reversed. Okay, how to fix it? Your miss will only ask you to rotate your robot 180 degrees in the perspective view. Okay, a lot of you say in orthographic view you see my robot is in front, but I change the perspective view. Okay, it's you see from the back. Okay, because the z-axis already reversed in the perspective view. Okay. So last part is just this projection matrix. The metric part is not so important because in OpenGL you don't need to declare this metric explicitly. Okay, you just need to call the command. Okay, and how to get this? So you have a set of formula there. So this is not max class. Your miss will teach you this way. This one is your MX. How to get this until here. Okay, so don't worry, you will have this kind of question. Okay. So this one is your projection. Okay, when you're given if you are given this perspective projection matrix, but your miss won't come up so hard like this if I give you the values, okay, I give you all these values. Don't this is not max class. I won't ask you to put in the value and give me the value here. So like your left right default one is -1 and 1 your bottom and top is -1 and 1, and then your new far, okay, is -1 and 1. I don't give you the default value and then ask you to put in the formula here and give me the value. Okay, no, that one is mathematical. Okay, but you have to know this is projection for matrix for perspective. When I say compare, okay, is this auto or perspective? You should be able to tell this one is perspective, and then that one just now is auto lah. Okay, compare, this one is auto. Okay, but what this formula, how to get this formula? Okay, no need to memorize. Okay, you will be given, but normally your miss won't. You can see your past question, but your miss don't ask. Very rare or ask matrix. I only ask once time. Then one time already see not so many students can do, and then don't want to ask anymore. Okay, when I put the value here, then you guys don't know what is that. Okay, with this one actually we done the chapter 5. Okay. Okay, this one perspective view for geofrustum. So you draw one small. Okay, your new plan. Draw one big, your far plan. Then at the end, okay, it will convert your projection line will convert at the second point here, which is your camera or your eye. your view. Okay, then is this one is your, after you place your grouping module, it means it come to your clipping. Okay, your grip coordinates. Okay, you have your left, right, lor. Left, right. Same with your auto lah. Left, right, bottom, top, near, far. Okay, left, right, bottom, top, and then your near and your far. Okay, so that's all lah. This one your miss don't want to spend so much time. Later we do practical 5, then we can understand more. Okay, your miss will show in the practical class. So we have to start chapter 6. So we done chapter 5, viewing and projections. Okay, if you have further question later, you can ask during your tutorial class. Okay, it's always so fast. You know, I cannot finish, then your tutorial also cannot do.
Then no need to.
So your midterm test will only until chapter 5, chapter 5, but we cannot do yet because tutorial 5 haven't finished. Practical 5 also haven't finished. Okay, so most probably will be next week. Cannot.
Cannot.
Week 10.
Can.
Week 10 one more week.
Yes.
Okay, your midterm.
Therefore,
Next week we can finish all chapter 5, practical 5, tutorial 5. We will go chapter 6 already. Okay, chapter 6, lighting. Okay, lighting. So the first two color materials, we actually looked at it before in when we do geometry primitive. Okay, we will go through again. Okay, these chapters. Okay, when we implement lighting. Okay, how the lights will affect the colors and the material. Okay, so these are the 4 things. Okay, will be covered in chapter 6. Okay, illuminations and lighting. Okay, when we say lighting, you cannot run away with your normal vector. Okay, normal vector. Okay, how to calculate the normal vector. Okay, we just learn the concept lah. Okay, so all this, like the mathematical calculation parts, is really done inside the OpenGL libraries. Okay, you just have to call the commands. Okay, so you understand the concept is enough. So how to get the formula and then calculate part, okay, that one is not the main purpose of this course. Okay, so we have to use the command and then do it in our practical. So last part is the material properties and object shading. Okay, we go through again the object shading. We have learned last time the flat shading and the smooth shading. So now is in lighting. Okay, how it works. Okay, material properties is colors lah. We got see color before. Okay, so when come the color, you cannot run away with lights. Okay, if no light, you cannot see color. Okay, our lighting spectrum. Okay, colors. This one is spectrum already. Okay, so those colors is actually visible lights that you can see with your human eyes. Okay, these are the regions of lights that we can see here, the spectrum. Okay, there are other lights that you cannot see, other wavelengths like gamma rays, X-ray, infrared, microwave, radio frequency. These are the lighting that is not visible with our human eye. Okay, human eye only visible for this wavelength of the lightings where you can see the colors of our spectrum. Okay, I think this one last time you go to experiment already in your size. Okay, that's why we have a rainbow. Okay, you know why we can see rainbow on the sky? Because got lights. Okay, strike on it, then you can see color. Okay, questions, colors. Okay, is black a color? Is white a color? Yes, no? Black and white is color or not?
Yes.
You say yes because in kindergarten my teacher tell me color black color, color what colors? Then you will say it's a color. Okay, in graphic terms, okay, in graphic programming, graphic terms lah. Okay, black is not a colors. No, it's white. Okay. So when you see black, mean there is no color, absent of all the colors. When there's no light at all, you see totally black. Okay, you go inside the room. Okay, at night, don't have lights. You close everything, then you cannot see anything. Black. You see black. Okay. So white, okay, is the combinations, the even combinations of all the colors together. Okay, that's why your RGB, if you say no colors, 0, 0, 0, black, you get black. Okay, so when your color all even, 1, 1, 1, you get white. Okay, so white is then even combinations. When you want to see color, must have lights. No light, you cannot see. You go inside the room without any lights at night, you cannot see anything. You even cannot see yourself. So which means that the white objects is the one that reflects. Okay, reflects all the wavelengths. Okay, those very bright objects, you can see. Okay, it actually reflections. Okay, all the wavelength of the lights of the color, then you see white color. So black is the object that already absorbs, okay, all the wavelengths of the color evenly. Okay, so when you see colors here, it's RGB. So all color don't have 0, 0, 0, you get black. All color evenly 1, 1, 1, you get white. Okay, remember this. Should be easy lah. So when the light strikes, okay, on the object, this is your object. Okay, the ray come. The lights come. Okay, there are 3 things will happen here. One, the absorptions. Okay, the lights fully absorbs into the objects. Then you see totally dark. Okay, or you see fully reflections, totally reflect. And you will see very bright objects here, shining. Okay, or reflections. Okay, part of it, okay, will be absorbed this face, and some of it will be reflects. Okay, that's reflections. Okay, 3 things that will happen when the light strikes on the objects: reflections, absorptions, and reflection. See here. Okay, absorb. Okay, reflect. Okay, so when you reflect, you have this theta. Okay, this is a AOI angle of incident. Okay, we'll see later. Okay, so this one reflection. Totally reflect. Okay, so light come to objects, so either absorb, either reflect, or either reflect. Okay, 3 things. So what we can see on our eyes, okay, it depends on the amounts of the lights, okay, that come to your eye. Okay, if there is no light to your eye, close all the lights here, no sunlight, night, cannot see anything. Okay, move on to seeing, must open your lights, we cannot see. Okay, so and how the things look like, your objects look like, okay, it depending on the light source, okay, where you put your lights there, okay, and also your surface, okay, your surface properties. You can see the same room, okay, with the same object, spheres here, there are spheres here, but the different placings of the lights. Okay, from the top, okay, where's your light source? Okay, and the intensity of the lights. Okay, when we say light source, okay, there are 2 things to mention here. One is the positions of your light source, where you put your lights. Okay, second is the intensity of the light source. Okay, what is the colors and how strong of the lights. Okay, surface properties. Surface property, you can see compare here. Okay, you can see fully reflections. Okay, all the colors of the wall, you can see fully reflects on the surface of the sphere here. Okay, however this one no. Okay, fully opaque, no reflection. Okay, so all the light source already absorbed. You see the objects only, you cannot see this red color, the wall colors here in your sphere. Okay, and this one is look really dark, but still can see with some reflections here, red color. Okay, so the material of the object are different. Okay, whether it's a very shiny object, shiny material, okay, like glasses, okay, mirror glasses, or it's just a chair. Okay, this one, okay, opaque materials, rough surface, smooth surface. Okay, material property will depends also how the appearance of the objects, okay, in your eyes. So why we need lighting? Okay, actually from chapter 6, 7, 8, 9 onwards are all those graphic techniques. So lighting is one of it, is to make your graphic image more realistic. Okay, so before you implement any lighting, like your particle that we did previously, so you draw your cube, you draw your sphere, it look very fake, not realistic. Okay, look like 2D circle. Okay, so then your miss ask you how we can make this 2D circle look like sphere. Then we try to rotate, also look like 2D. We try to color it, red color, it still look like 2D. Okay, then to make it 3D, what we did last time, we just change it to wireframe. Okay, so other than wireframe, okay, now your chapter 6, 7, 8, 9, 10 all can make your sphere look 3D. Okay, your chapter 5 is the perspective view. Okay, if you use perspective view, your sphere will look 3D. Okay, chapter 6, you implement lighting, then your sphere will look 3D. Okay, you no longer see look like circle, you know it's a sphere. Okay, you can see this teapot lah. Example here. Okay, this is the one that we create all the while. Look like this. The teapot is 3D, but it still look 2D. Okay, so you put lighting, much more. You can see much more bigger improvements of the graphics. You can make 3-dimensional 3D appearance. Okay, make it look 3D already. Okay, after putting lighting, it's already look 3D. No lighting, this is what we did last time. You draw sphere, it also look like circle. Okay, this one draw teapot, also look like 2D. Okay, so you add lighting, and you get 3D and more realistic. Okay, so these are the 3 basic lights. Okay, this one you have to know. And we will also implement all this in your practical, and you have to apply in your assignment. Okay, the 3 types of lighting in basic lights in OpenGL. Okay, we have ambient, diffuse, and specular. Okay, see one by one. You can see the differences here, very easier to see. You can see the black color line. Okay, these are the ray, the light source. So for ambient lights, okay, the light source come from all directions. Okay, the black color, all directions, and then the white color are the reflections. Okay, and it will reflect evenly in all directions. This is the ambient lights, or we call it as global lights. Light source come from all directions. Reflection also reflect in all directions. Okay, this is ambient. Okay, diffuse and specular. Okay, these two are, you see the light source is directional lights. Okay, from one direction, the black color arrow. Okay, the differences here between diffuse and specular is their reflection. Okay, for diffuse lights, okay, the reflections are in all directions. Okay, however, your specular lights is fully reflected in one directions. Okay, specular, so this part will look extremely bright. shiny, fully reflected, your light source. Okay, that is specular. Okay, we'll go into one by one now. Let's start with ambient lights. Okay, ambient lights. So used to model light source that come from every directions in the same intensity, or we call it as global lights. Okay, like your sun. That's sunlight. Okay, that's global light. So I mean intensity, intensity of ambient light. So you can have the colors of the light. Okay, RGB, red, green, blue for your ambient light. Okay, so this is the objects. Okay, let's see object here. I can see. Okay, this one X, X object X. Okay, you apply blue color ambient lights. Okay, this is how it looks like. Okay, the teapot. Okay, you go and apply red color ambient lights. Okay, intensity red color ambient lights. Okay, this is your teapot. Okay, after you apply your ambient lights, then you go for diffuse light. Okay, diffuse lights. Okay, so same thing, intensity of your diffuse lights you define with your red, green, blue value of your diffuse lights. So it's used to model the light source that reflected from the object with extremely rough surface. Okay, and the light source will reflect evenly in all directions. So after you apply the diffuse light, you can tell the directions of the lights. Okay, because this is a directional light source. Okay, you can see here lah, this one X. Okay, you see this part is brighter. Okay, the left side here look darker. So you know your light source is from the right. Okay, and your teapot here, you see bottom look darker. Up here look brighter. So your diffuse light is from the top. Okay, here look dark, here look bright. Okay, this one it implement the diffuse lights. The next will be the specular lights. Okay, specular lights normally used to do a highlight, highlights. Those extremely very shiny one, you see the dot there. Okay, used to model the light reflected from object with extremely very shiny surface. Okay, smooth and totally reflects very bright. Okay, see this. So for the X object, this part are the one with the specular lights. Okay, SP means specular lights, so I is intensity, so RGB, red, green, blue. Okay, so for the teapot, this part will be the specular lights. Okay, the extremely shiny surface is this part. So when you shine the directional lights of it, okay, then you will get the shininess. So normally we will implement all the lights together, we'll combine. Okay, not in one lights. That's why you always say, I want all the lights. Ask you one in your assignment when you demo. I mean, you got ambient lights or not? You got diffuse lights or not? Do you have any specular lights? Show all 3. Okay, so these are the teapots with ambient lights, diffuse lights, and then you add in specular lights. Okay, at the end, this is how it looks like. Okay, which look realistic. Okay, same for your this X object, ambient, as diffuse, as your specular. And now your object is look really nice, realistic, and 3D. Okay, when you implement all the 3 lights thing together. Okay, this one to perform the lightings in OpenGL. Okay, your miss will explain briefly first, then later we will do together in OpenGL. Okay, when we do practical 6. Okay, so to perform the basic lighting, okay, you see that this one OpenGL window, the object already have the 3D, the lighting, so it's look realistic and it's look 3D. So 3 steps here. Okay, these are the 3 steps that we're going to do in practical 6. Okay, first thing is to enable lighting. Okay, enable lighting means you turn on your lighting, then specify Okay, specifying your light source properties. Okay, where you want to put your light source, the position and intensity. Okay, what color of the light source and where to put it. Okay, then third step is to provide the information about the surface. Okay, this one is shiny surface or is a rough surface. Okay, so 3 steps. Okay, going one by one. Okay, to enable lighting very easy, just call GR enable, GR lighting. Okay, if you want to turn off the lighting, then GR disable. Just like the switch lah, just like the switch. Okay, enable, disable, on off lighting. First step lah. Then after this, specifying light source properties. So 2 things, position. Okay, X, Y, Z lah. Where you want to put your lights, here, 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 anyway. Okay, then intensity. Okay, intensity, specify the types of the light source. You want ambient lights or diffuse light or specular lights. So this is the command, GL lights FV. Okay, float. F is float, V is vector. Okay, the vector here, if it's position, it will represent your XYZ. So if the vector here, you are setting the intensity, then it will represent your RGB, red, green, blue. Okay, then you pass in your light source. Okay, the types here, the parameter name will be ambient, diffuse or specular. Then this is the value. Okay, this command we will go through again. We do in the Article 6 later. Okay, so you can set up your lights as a directional lights for diffuse lights. Okay, can be point lights or spotlight. Okay, but your mains no need point light and spotlight lah. We use global lights and also directional lights is enough, because this one you have to set your angle of your spotlight. Okay. Okay, we do the basic lighting is enough. Okay, next is to provide the information about the surface. Okay, you can see this sphere with different surface, how it reflects with the light source. Okay, so different appearance with different material properties. So when we have material properties, then next is the surface normal. Surface normal. So if you use flat shading, your surface normal will be identical. Okay, so it will attach to the first vertex. Okay, this one's surface normal. We see in the next slide. Okay, how to get the surface normal. Okay, so the angle at which the rays of the lights hit the surface, okay, we call it as AOI, angle of incidence. Okay, so the angle of incidence will affect the brightness of the surface. Okay, you see this paper, this one is paper. Okay, this is a paper. Okay, if you put on your table, okay, facing the light source. Okay, so your AOI is 0 degree. Okay, then you can see very bright your paper, test pad. Okay, got line here. Okay, however, if you take your paper, your notepad, you go and put it like this, okay, 45 degree, then it's likely to look dark or gray color. You cannot see this part. Okay, so this one AOI 45 degree, this is how you look. Okay, same thing lah. If you open the door, your light is here. Okay, we stand at the back of the door. Okay, 45 degree. The one at the back of the door will look very dark. Okay, the front here, then will look very bright. The one that facing the light source. Okay, same thing. So affect the brightness. This one AOI 45 degree. Okay, so in order to calculate the AOI, so we first need to know the directions that each surface is facing. Okay, normally the surface that face the light source, directly face the light source, will look brighter. Okay. Okay, but now the light is at the top. Okay, surface, so on top will look brighter. Okay, if you go down, then you don't have the box. Okay, the one at the bottom one will look dark lah. Okay, so if your light source is from the side, Okay, then you have your box here. You have your box here. Okay, normally the surface that facing the light will be look brighter. Okay, the one that at the bottom and at the back one, not facing the light source, will look darker. Okay, and you draw. Okay, you draw 190 degree, one vector, draw one line. Okay, from the surface, let's see this cube, this plan. Okay, you draw one line up from the surface, 90 degree. Okay, this one will be the surface normal. So if your surface normal is facing the light source, your light source is here, definitely this face will look bright. Okay, so if you face it, if your surface normal, like at the back one is facing another side, then your light source is this side, definitely that one will look dark. Okay, so the direction that the surface is facing, we call it as normal of the surface. Okay, normal are the unit vectors that are 90 degree. Okay, to the surface. Okay, this one is your surface. This line, the surface of the objects. So you draw one line up, one vector up with 90 degree from the surface. This is your normal. Okay, normal. Then this is your light source. Okay, the lights are L. Okay, so the angle between your light source that hit the surface and your normal, this angle theta, we call it as AOI. Okay, angle of incidence. So a normal is a vector that point in the direction perpendicular to the tangents of the surface. Okay, here this one use L here, use N here, but inside the formula is use other alphabet. Never mind. Okay, so if it's a plan surface, like our cube or our pot, if it's plan surface, very simple to draw the normal. Okay, from the surface. Okay, if you only draw one up here, okay, in the middle of the surface, okay, this is smooth shading. Okay, so for flat shading, your normal is only draw on the first vertex. Okay, normal at different point of the surface are identical. So for plan surface are identical, mean all this whole surface will share one normal. All this whole surface, the whole quad, okay, will only have one normal. Okay, however, for curved surface, let's see this curve. Okay, your sphere lah. Curved surface, you have many vertex, right? Okay, each of the vertex also have one normal. So you have many normal for curved surface. So different point may have different normal. Okay, when more normal mean more calculations, more expensive, and then your quality will be better on the lighting and the shading. If less normal, less calculation. Okay, but your quality not so good lah. Okay, you can compare this one later when we do practical on the flat surface and on your sphere, your curved surface. Okay, the two shading can see here. So for polygonal mesh, the normal vector are often associated with the vertices. So normal will put on the vertices there, then you attach your normal rather than the polygon face. So for flat objects or flat shading, okay, the normal vector are identical if you only attach on the first vertex. Okay, so not so good lah. You can see here. This is flat shading. This is what you get. You still see the line. Okay, the box. Okay, not smooth. Okay, smooth shading. Okay, smooth objects, so normal vector can be different. Okay, you attach to each of the vertex, then you get much more smoother. Okay, this one Phong shading is the best one. Okay, later we will see the tree shading. Okay, flat, smooth, and also Phong. normal. Okay, you see this surface is a triangle here. Where is a triangle? So you have your 3 point here, your point 0, point 1, and point 2. Okay, so this surface, this triangle, you draw one vector up. Okay, 90 degree. This is your end. Okay, your normal. So how to get this normal? Okay, this is the formula. Your normal will equal to your P2 minus your P0 times your P1 minus your P0. Then you get this normal. N. Okay, a normal from a flat surface. Okay, so however for curved surface, okay, the one just flat surface is very simple. For curved surface, you need to use quadratic trigonometry. Okay, your cos and sins. Okay, in the implicit equations, okay, x squared plus y squared plus z squared minus 1 equal to 0. So if you heard people say UV here is to calculate the lighting. Okay, so the coordinates for your light source. Okay, we didn't use x and y, we used u and v. Okay, so your x will be your cos u sin v, and your y is your cos u cos v. Your z is your sin u. And don't worry, this one your miss won't test you. Okay, because in OpenGL you don't need to give the equation just now. Okay, no need to give. Okay, you want to attach normal with your vertex, you just have to call this function. Okay, GL normal 3F. Okay, 3 floating point, passing your nx, ny, and nz. Okay, or you can put your xyz in a vector, then GL normal 3FB. Okay, like the cube, so we already draw this cube. You already draw the cube in your OpenGL. We already draw the cube. We have 6 surfaces here. Okay, so if you want to attach the normal on each surface, we have total 6 surfaces. You see the green color. Okay, you want to attach, then you just put your GR normal 3F. Okay, 0, 1, 0. Okay, attach here. Then you draw your top face. This is your Y. Okay, you put your y 1.0 here. Okay, then you draw your right face. Then your right face, you put your x 1.0 lah. Okay, this one you can try later when we apply lighting. Then you draw your cube inside. Then you can see when you didn't attach normal, you didn't call GR normal 3F. Okay, what happened to your cube? Okay, and after you call GR normal 3F, okay, what you can observe from the cube. Okay, ambient reflections. So we start with the reflections. Also formula, you will see a lot of formula here. Okay, how to calculate the reflections for ambient lights. You can see reflection for ambient lights in all directions. Okay, so holding green. Okay, and the ambient lights is the one will give the colors for the objects. So if the object don't have colors, okay, whatever light source colors that you cast to the objects, then the object will look that colors. Okay, because it's evenly, it reflects evenly, so the whole thing look one color. Okay, this is ambient lights. Okay, so to model the ambient light reflections, so this one is the intensity of the ambient light reflections. So it's calculated by the ambient. This thing is called reflection coefficient of ambient lights. Okay, multiply with the intensity of the ambient lights. Okay, the coefficients, you time the intensity, then you get the reflection. Okay, the formula actually is the same. Later you go to the, we of the light source, and then this one is the reflection coefficient. Then at the end you get the reflections of the ambient lights. Okay, next it will be the diffuse lights reflection. Okay, you can see different just now with the ambient lights. So just now ambient light holding look greener, one colors, but now after diffuse light you can see this part brighter and this part darker. Okay, light source come from here. The light source come from this side. Okay, diffuse reflectors, okay, will scatter the light source equally in all directions. Okay, your reflection just now for diffuse will be all directions. Okay, compared to specular. Okay, the difference for diffuse and ambient diffuse is directional light source. Come from one. Okay, your ambient light is come from all directions. So in this Lambert law, got mentioned this. The intensity of the lights that reflected here, okay, is proportion to the cosine of the angle between the light source and the lens surface normal. Okay, draw one normal, the angle here, so it will be the cos theta. Okay, so for diffuse light refraction, this first part is similar with the ambient lights. Okay, intensity, this one reflections of the diffuse light intensity is similar to the coefficient, okay, reflection coefficient times the intensity of the diffuse lights. But for diffuse light, you have this cos theta, cosine of the theta here. Your theta is the between your light source, the angle between your light source and your normal. This one, okay, here. Okay, the theta. So you have to time one more, which is the cos theta. Okay, it got mentioned here lah. N is the normal and L is your light source intersections to the light. Okay, here, theta. Okay, so for diffuse lights, only this part different from the ambient lights. Okay, so for specular lights, it's almost similar with the diffuse lights. Okay, more or less similar. But what happens here, because it's a shiny, extremely shiny surface, you see this part. Okay, this is where the specular lights happens. Okay, it's extremely shine. Okay, fully reflections. Okay, the coefficient value is very high. Okay, so shiny surface have a high specular coefficient, so it's used to model the specular highlights for shiny objects. You can see totally reflect. Okay, smooth and reflect out. Okay, so the formula same here as your diffuse lights to calculate the specular light reflections. Okay, just the difference here is this F values. Okay, your cosine here, you have this exponential value, the F here. Okay, that's the experimental adjusted positive constants to make your reflections, your coefficient reflections to be very high. Okay, the rest of the things same. Okay, your reflections of your specular light same with your coefficients. Reflection coefficients of your specular light times your intensity of your specular lights, and then the cosine. Okay, cosine theta is the angle between your light source and your normal. Okay, and then you have this F. Okay, this cosine you can change to dot product between your R. Okay, your R is here. Okay, and your V. Okay, your V is here. U is your light source, your V is your normal. Okay, so different F value, you will get different reflections. So you adjust your F value here, the parameter F, the exponential value, you can see from 1 to 50. Okay, 1 is a very high. Okay, you see very bright here. Big area. This one with the F value equal to 1. You can see your normal. This is your R, the angle, your light source and your normal. So you adjust your R and V, this angle, your light source angle. Okay, your theta. So this is what happened. Okay, when your F come to 50, okay, your specular light now not so high, the reflection not so high anymore. Okay, so this one is the F values for the specular light, sir, that you adjust between your R and your V here. Like that. Enough now. 3 o'clock already. You guys didn't tell your miss out. Then your miss will talk. Okay, last part a bit. Okay, drill. Then your miss stop here lah. Got a bit. Okay, finish on lah. Okay. I will stop here at slide 34. So last part is the material and the tree shading only. Okay, this one we continue next week. Okay, flat shading, gerak shading, and palm shading. Okay, see the apple. Okay, your miss will stop here at the specular lights coefficients to calculate the reflections intensity.